We are group 37 and this is our project Heimdall, where we compare the performance of convolutional neural networks with vision transformers for land use classification. The reason we chose this project is very simple. Land use classification plays a very important role in many subdomains like urban planning, environmental monitoring, and disaster recovery. CNNs have been the long-standing standard for image classification in this particular subtask, but more recently, vision transformers have started to excel at this, especially for certain kinds of land images. Our problem statement is simple. We want to compare convolutional neural network architectures, so state-of-the-art convolutional neural network architectures, with vision transformers for land use classification on two data sets. The first dataset is the Eurosat dataset, which contains 27,000 RGB images, which have a 64 by 64 pixel resolution. And the second dataset is the UC Merced dataset, which contains 2100 RGB images, which have a higher resolution, so 256 by 256. The output of our model is a probability distribution on each of these classes, so 10 for the Eurosat dataset and 21 for the UC Merced dataset.
The evaluation procedure that we followed was basically analyzing the confusion matrix and the analysis of the frequently misclassified classes by the models. We also tracked the performance of the models using accuracy F1 score and class-wise accuracy as well. We monitored the inference speed as well as the VRAM consumption during training. As our baseline, we chose the efficient net B4 convolutional neural network, which has 19 convolutional layers across 7 stages of MB-conv blocks. Trained this model for 30 epochs at a learning rate of 10 raised to minus 3, and we use the Adam optimizer for that. For our loss function, we use the cross entropy loss, which is ideal for a multi-class classification task like we did. The hardware that it was trained on was the NVIDIA RTX 3050 GPU and the T4 GPU on Google Colab. On the Eurosat dataset, our baseline model achieved a test accuracy of around 92%, and the C-Lake class was the best performing class on this dataset. On the UC Merced dataset, we achieved a baseline model test accuracy of around 72%, and the forest class was the most accurately identified class by the model. Looking at some classes that were frequently misclassified by the model, on the Eurosat dataset, the permanent crop class was frequently confused with the herbaceous vegetation class. We also monitored the inference speed of the model on GPU as well as CPU. Similarly, on the UC Merced dataset, the most frequently confused classes were the dense residential class and the mobile home park class.
So here we have the description for our vision transformer model. We basically use Google's VIT base model, which uses 16 by 16 patch embeddings and yields a sequence of 196 tokens. These features are embedded into a 768 dimensional vector, which then follows a linear head for classifying the image into one of 10 classes for the Eurosat. The model has around 86 million trainable parameters. The training strategy was training it for 30 epochs with a learning rate of 10 raised to minus 3 with the Adam optimizer, and we used the same reduced LR on Plateau rate scheduler. The loss function we used for the vision transformer was cross entropy loss, and we trained the model on Google Colab's T4 GPU. So for the vision transformer model, we don't see a lot of improvement on the Eurosat, but we do have an increase in overall accuracy to 93%, and the top prediction class, or the top class with the best performance metric, is still C-Lake class. We do see a substantial improvement on the UC Merced dataset with an accuracy of 88%, up from the earlier 72%. And if we look at the top confused pair class for the Eurosat, it still is the permanent crop and herbaceous vegetation class, which leads us to believe that the vision transformer isn't really able to work that well on low resolution images. Whereas on the other hand, for high resolution images, as we see in the UC Merced dataset, we see a substantial improvement in the overall predictions, and the top confused class pairs are just the storage tanks confused with the intersections. So overall, our key takeaways are that vision transformers do outperform CNNs on both the Eurosat and the UC Merced datasets, but specifically for the UC Merced, the vision transformer is able to benefit from the higher resolution images, with the test accuracy improving from 72 to 89%. These are some of the references, and thank you so much for your time.